Good afternoon. Let me introduce you to Olof Kindgren. Olof is a digital design engineer working for Qamcom research. And he's also co-founder and director of the FOSSI Foundation. I met Olof some years ago when we started the RVFPGA project, where in fact he's one of the main contributors. And we've kept in touch since then and kept collaborating. In 2023, he was awarded by the RISC-V International, and he's currently a RISC-V ambassador. As a developer, he leads several open source silicon projects that you probably know, such as FuseSoc, VirWolf, Serve, which is claimed to be the smallest RISC-V CPU in the world, and I trust him. Y bueno, pues quería decir simplemente que muchas gracias por aceptar esta invitación y espero que disfrutes mucho de Madrid y que mejores tu español, que ya es muy bueno.
Gracias por eso, Dani. So, es mi primera vez en Madrid. Estoy aprendiendo español en Duolingo, pero esta charla voy a estar en inglés. So, welcome. Thank you for having me. So, as Danny said, I'm having problems with this thing. Let's see if I can. That's my bad. Yes. So I'm working for a company called Qamcom in Sweden. We do a lot of interesting things. Look us up if you want to know more. I will not go into more detail. Because the reason I'm here is that I am very involved in open source silicon and have been for the past 15 years. As a developer, I lead many projects, way too many for my own time. We will touch upon a few of these in this talk. I'm also an advocate for open source silicon, co-founder and director of FOSSI Foundation, helping out with a startup called ChipFlow, our RVFPGA contributor, so together with Danny, RISC-V ambassador. And last year we had a paper published in Nature around my Serve CPU, which was picked up by PC Gamer. So now published in PC Gamer also, which I think is quite nice. So we're going to talk about open source silicon, and I think we'd like to start with making a distinction here that open source silicon is not open source software and is not open hardware. When we talk about open source software, I think most of you have an idea what that is. It's source code, it's software. It can also be documentation and other assets. Open hardware, on the other hand, is physical things. We can have open hardware buildings. We can have things that you 3D print, physical things, chairs, other kind of objects. And open source silicon sits somewhere in the middle because a lot of it is software. When you're doing simulations or we have EDA tools or things like that, design IP. But it's also about realizations in hardware when you make an ASIC, for example. And there are special regulations that are required for this. We have special laws like the MASC Act, which is specifically for chip design. So we try to say that open source silicon is about code that is written in HDL, like Verilog or VHDL or other, we will get into later. Can be other design sources. When you do an analog design, you have your layouts, you can have net lists, and it's also tools for working with these formats and information needed to produce the chips, which is often the PDK, but can also be other things. Another thing I would like to say is what open source is not, or open source silicon is not. And this is a famous quote by Henry Ford. He said, if I had asked people what they wanted, they would have said faster horses, because they knew the horse, they knew what that was, and they wanted just something that was better than what they already had. In fact, this is probably bullshit. Henry Ford never said that, but the thing still remains that if I ask people what they want a cheaper model sim, or VCS, or Xilium, because they often want something they already have, but they don't want to pay for it, basically. And I think that's a very narrow thinking, because open source is not a faster horse. What we can do with open source is much more than we can do with the proprietary things. Linux didn't win by being a better Unix. It won by enabling new business models. If you had gone to Sun Microsystems in the 90s and said, I would like to buy 1 million Unix licenses to put in my router or in my phone, they would have just not been able to do that, because that's not how their business model worked. But you could take Linux and you can do all these things. You could enable new things that you couldn't do before. So open source doesn't win by being better. It wins by enabling new business models, accelerating innovation, and adapting to change. Because once you give the tools to the people, they will come up with things that you have never thought would be possible. And when we're talking about open source silicon, one way to look at it is to divide it into three very distinct parts. Design IP, EDA tools, and PDKs. There are other ways to look at this, but this is the way we will look at this today. And things work best when they are all open source, but that doesn't need to be that way. I mean, for example, I know many companies that are using open source EDA tools and an open source PDK, but they have the closed source design. Or they have an using primarily open design IP, but they're using proprietary tools and the proprietary PDK, and so forth. So you can have a mix of these. We don't need to have all three, but the more we have, the better, generally. So if we start looking at one of these things then, we started looking at open source design IP. I learned sometime that the fastest way of doing something is to not do it at all. And this goes for development as well. If you have something that you can reuse, then it will be much faster than doing it from the beginning. And both for software, it's obvious. You don't start, if you start a C project, you don't start by writing your printf function. Or if you have a Python project, you don't start by reinventing all these libraries. You just take them and then you build your thing on top of that. And this is what I wanted to be for chip development as well. You want to be able to use a lot of commodity IP, and then we can add our special thing on top of that. So if you have all your CPUs and the bus infrastructure and peripheral controllers, SPI and I2C and things like that, just be able to pull that in and then build on top of that. And when I have IP, we typically have them from many different sources. It can be that we have developed them ourselves, or they came from the platform vendor, or you have bought them, or you're picking them from open source. And in order to make this efficient, we need to have a way to easily reuse these things and share also with other people if we want to do that. So this is where I come to one of my projects that I've been working on for the past 13, 14 years, which is called FuseSock. And the concept is very familiar if you come from the software world with a package manager, where if you're using Ubuntu, you apt install something, and it will take care of all the dependencies and everything that package needs. Or if you're using Python, you pip install something, and then pip will take care of everything for you. And the same thing with FuseSock. If you depend on a CPU, for example, then that CPU will know what extra things it needs internally. And it will be hierarchically build up the dependency tree. So you can mix your design sources from a lot of different places, and you can reuse open source things, and you can use your in-house developed things as well as you want. Also, the other part of the equation is when it comes to the tools. And that's a big difference from software world, where if you have a C program, you probably run it through one compiler, GCC or LLVM, or maybe some other tool. But in the EDA world, we might have 5 different simulators we want to use the same code for, and then couple of different FPGA tools, or we want to do ASIC synthesis. And FuseSock allows you to use the same description, same core description, IP core description to target, currently I think it's 40 plus different EDA tools with one description. A project like this only works if you have a large pool of packages, otherwise you're just starting from scratch anyway. For FuseSock, I know that there are thousands of FuseSock compatible packages out there. I can easily count to 1,000 just looking at available online sources. And the way FuseOC is constructed, I don't know all the cores that are available out there. I would need to look them up, but I have identified that there are at least 1,000 I can find myself, but probably more. And then I know, because I do contract work for customers who are using FuseOC, so I know that they all have thousands of cores inside their network on their products. And many of those are also relying partly on open source tools. Like the OpenTitan project is integrated into many different products. Big challenge: trust and quality control, and support and maintenance. It's very easy to write code. It's much harder to actually make sure it stays relevant. And the maintenance problem is something that everyone needs to be aware of, and that we need to have a better way of taking care of code. So the idea is that no one needs to make another UART or another CPU. They just reuse one. Unfortunately, I forgot about that and made a UART myself. But only because I wanted to see if I could make a UART with the source code that fit inside a tweet. This was before Twitter was taken over by crazy people, to my defense. But I made a datasheet also, so I at least made a bit of documentation for it. And I also happen to make a RISC-V CPU. In fact, I made the world's smallest RISC-V CPU. And I will not go into much detail here. I can do a whole presentation on the server CPU itself. You can probably look it up online. But one thing to notice is that, again, when I made this thing, it was mostly for fun. I did it on weekends and evenings. But it has been picked up by the industry. It's used. One of the coolest things, I think, is the Fraunhofer Institute has used it in a cranial implant. It was also done on printed electronics, which was the base of that Nature article I showed you in the beginning. And I use it in FPGAs in different places, and then it has been used in multiple ASIC implementations as well. And yes, it runs Doom also, at about 4 seconds per frame, not frames per second. It's not fast. So that was mostly digital IP, but if you look at the analog IP, the situation is even harder in one way, because the pool of developers is even smaller than they are for digital IP. And it's very niche, it's very complicated in many cases. And again, we say that open source is not a faster horse. We don't want to just have everyone making all these IP, because that would not be feasible. We can't make the analog IP as fast as we would like. So what we do instead is that we use software. We see if we can instead generate these things. We have projects like OpenFastSoC, OpenRAM, PDK Master, Berkeley Analog Generator, GDS Factory, which all in different ways generate designs. And this is a software thinking of approaching this problem. GDS Factory is apparently used a lot in photonics. They are super happy about this. I don't know that much about the project, but I do know that photonics people are very happy this thing exists. And I don't think this is one of the things. This was completely unexpected that the photonics industry would pick it up. But once you make things available, people will find it, and it will be used in ways that you maybe have not anticipated. Another big part is the EDA tools. That's the second part of what I described in the beginning here. And if we go even further down, we can divide EDA tools into different areas, and verification being one of the more important ones. We see all the time that verification is becoming such a big problem. The complexity of verification grows faster than the complexity of implementation. So we need new methods, and this industry talks about shift left, about doing higher level verification as a mean to getting done faster. And there are lots of different ways to do this. And I would like to single out Verilator as one of these very important projects. So if we look at the classical simulation tools, we have Xelium, VCS, and ModelSim or QuestaSim, and a few more. Those are the big ones. They can simulate the whole Verilog standard. And I don't know if has anyone looked at the Verilog standard? There's a lot of weird things in that standard, like things that you probably had no idea existed. But what Wilson Snyder, who made Verilator, realized is that actually most of the time you're doing synchronous designs which are digital. You don't need all these analog stuff. That's more like specific use cases. So what he did was that he focused on one use case, synchronous digital design, and could make Verilator much faster than any of the other proprietary simulators. Now, actually, what has happened is that Verilator now is actually starting to move into and taking on capabilities that the other simulators have. But for many, many years, it was just doing that, synchronous digital design. And I know big companies who have publicly gone out and said that they use Verilator for a lot of things. Because you can spin up a cloud instance, like you can spin up 1,000 Verilator instances. It will cost you nothing. You don't need to worry about license management and things like that. Another tool that I typically say is, I think will become one of the more important technologies in the coming 10 years is CocoaDB. So CocoaDB is a framework. On the technical side, it kind of embeds a Python interpreter inside your simulator. But what it does is that it allows you to write your test bench logic in Python instead of in Verilog or VHDL. And there are and you will still run it with a regular simulator, like Verilator or one of the proprietary ones, whatever you want. And your design is still written in Verilog or VHDL, so it's just for verification. There are three things that I think makes this much more successful. And the first thing is that there are a lot of more people who know Python than knows Verilog or VHDL. I think the people in here, you probably not like typical, probably know more about these strange languages than most people do, but I think they're probably 1,000 to 1 when it comes to Python engineers versus Verilog and VHDL engineers. And if you look at verification, it has nothing to do with band gaps or transistors or any of the electrical things. It's just logic, it's just functionality. So the idea is that if we can put software people on doing this, then we will have a much bigger base to pull from for verification. And the other big thing about Python in this context is that there are so much Python code written. You can easily compare your models against like a JPEG library or cryptographic library or some kind of machine learning library or things like that. Instead of having to reinvent all these things in Verilog or do some weird passing of things between the two worlds. And the third thing is more like a political thing, is that I mean, Verilator, that's a competition to the proprietary simulators. They lose business when Verilator grows. But CocoaDB, you still use your ordinary simulators. So the EDA vendors, they're actively pushing for CocoaDB. So CocoaDB is nowadays managed by the FOSSI Foundation, and we have deals with all the major EDA vendors where they are supplying licenses to make sure that CocoaDB works well with their tools. They have even their legal department have rewritten some of their header files just to make sure that it works well in an open source project. And this is a big thing. It's a major change. And we see that they are offering courses on CocoaDB. So I mean, one takeaway, this is something I would recommend you at least be aware of that it exists. I could go on and on and on, but I just wanted to mention a few other interesting verification tools. There are many, many more. Surfer, very modern waveform viewer that is picking up speed. Again, written by someone coming from the software world and was thinking about how would a software person like to use this tool and focus on usability instead of just taking the electronic engineer's view on how things should be. FireSim comes from Berkeley. It's a project where you can compile, well, you can simulate, or it's called emulation, I guess it's called. So you can run your designs instead of running in a simulator, you run it on an FPGA, but you can stop every clock cycle and you can get out waveforms and things like that. So it's hardware accelerated simulation. It was originally created together with the Chisel language and other tools from that group. But it works probably with any Verilog design nowadays. Again, I think this is, and it works on the AWS F1 cloud thing, or if you have your own FPGA, you can run it. So you can run it locally or you can run it on the cloud. Symbiosis, formal verification. I did some formal verification when I was in school at 2008. I thought it was amazing. I thought it was really cool. And then I went out to the industry and asked, hey, what formal tools are you using? And it turns out they weren't using any because they were too expensive. And I could not do it at home. I could not do formal verification because I didn't have any licenses. But Symbiosis changed that because it's a free and open source formal verification framework. So I mean, suddenly we have the option. I think formal verification is really starting to pick up because we have people who can, as hobbyists or in school, just try it out, learn a bit about formal verification. That's a big thing. And of course, we have classic things like ngSpice for the analog side. Again, many more things I do not mention here. If we look at implementation instead, one of the more well-known projects is called OpenRoad. And this is more closer to something that already exists. I mean, this is not a brand new idea. This is more like a re-implementation of what exists in the industry. It's a place and route tool, timing analysis, these kind of things for doing ASIC backend implementation. It was originally created through a DARPA fund in, I think it was 2018 or 2016, where they wanted to have a full, call it a 24-hour no human in the loop layout design project. So this should be a fully automatic flow for generating designs, ASIC designs. And of course, one is tempted to think that the open source tools lag behind the proprietary ones. But at ETH Zurich last year, there was a very interesting project called Basilisk, where they took a design that, as I understand it, they had previously taped it out using proprietary tools on a 130 nanometer process from IHP. And then they did the same with the open source tools. Found some problems where it was not as efficient. They fixed those. And I don't have the numbers here, but I think they came in like roughly a few % away from the PPA metrics of the proprietary tools. And this was for I can't remember if it's 100,000 or a million gate, but it's a Linux capable SoC they built. So it's a real design. And I think that shows also that I was surprised when I heard about that because I didn't realize how good these tools have become. And one thing, I mean, from a scientific perspective, there are a lot of people who want to do research on these kind of algorithms, place and route and things like that. And before, they have had to have NDAs, either had to invent their own tools from the beginning, from scratch, or they had worked together with one of the proprietary companies. And then they were forced under NDA not probably to release much of their research. But what happens now is that there's an explosion of people who are doing research around these tools and can try out novel algorithms. They can publish them. They can get real world usage on them. And they don't need to reinvent everything. They can just focus on the things that they are interested in. So I think these tools will evolve very rapidly. OpenRoad is, as I said, the backend part. We also have Yosis, which is a synthesis tool. And that is one of the tools that is created here in Europe by a woman called Claire Wolf. She actually did it as her bachelor thesis, I learned a couple of years ago, and I was like, that was better than my bachelor thesis. And this is the synthesis tool that all research is done on basically nowadays. Because it's openly available, it's plug-in friendly, and people are just trying different things and focusing their research on different areas of this. Same people around who are active in Yosys also did Next PNR, which is a FPGA place and route tool. And if you combine those two and add some more, we have F4PGA. I think it's FOSS. I can't remember what the 4 Fs are for. FOSS tools for FPGAs or something like that. Anyway, it's a whole end-to-end project from HDL to Bitstream for implementing open source implementations for FPGAs. And a couple of years ago, QuickLogic, which is a chip designer and they make FPGAs, they were the first company to announce that they provide an open source toolchain as the toolchain. Many of these are the ones like Xilinx. You can use, they have their official proprietary ones, and then you can use F4PGA in addition to that. But QuickLogic was the first one to say that this is the tool you should use for programming our devices. What has happened since is that Xilinx is actively helping out in this project, and also Lattice in some sense. So I think it's starting to open up. Traditionally, the Bitstream format has been a very tightly guarded secret from the FPGA vendors for absolutely nonsensical reasons, I would say. But yeah, we're getting there. And if you're not satisfied with the FPGAs that are on the market today, you can make your own FPGA with OpenFPGA. It's like turtles all the way down here. So this is the project for generating FPGAs, where you can define your lot sizes and you can define your interconnects and all these kind of things. And then it will generate your layout, and it will also generate a toolchain that can target these devices using Yosys and Next PNR or VPR, which is the other open source place and route algorithm or tool. VPR is actually the base for, I think it's Quartus, Altera's place and route tool is actually built on VPR, even if they don't say it anywhere. All right, so how many in here of you have used Verilog or VHDL? Yeah, most of you. Yeah, they're fine. They get the job done. Many people who are not in here would not be happy to use these unless they had to. But the thing is that this is the EDA tools. They only understand these languages, Verilog and VHDL. And VHDL is like very much a second-class citizen in many tools. But people realize that they don't feel productive writing in these languages. And there's nothing magical about these hardware description languages. I kind of get annoyed when people say, oh, there's not programming languages, there's a hardware description languages. Well, they are programming languages. It's just that we have decided that to give certain meanings to certain constructs. And the funny thing, if you look at the history of Verilog, for example, it was never meant to use for implementation. It was meant to emulate a circuit that you wrote on paper, or like you did the layout for manually. And then someone said, can't we use this Verilog thing to directly implement circuits? So that was an afterthought. So I mean, they were never used to implement logic from the beginning. So why can't we use other tools? If you like Python, then you can use Amaranth. If you like Scala, you can use Chisel, or if you use Haskell, you can use Clash, for example. And there are dozens of different tools. Still, the EDA tools only understand Verilog and VHDL. So all of these tools, what happened is that they compile down to Verilog at some point, and then they pass that Verilog into the EDA tools. So this is not optimal, and Verilog is a terrible intermediate representation language. I don't know how much you know about immediate representation languages, but it's kind of like an in-between language that is a description that is extra good for some operations. Like a net list, for example, can be seen as an intermediate representation language. It's a state that exists between the source code and the actual implementation. So what happens is that all these languages, many of these languages can now compile down to an IR, or an intermediate representation language. Next problem then is that there are almost as many immediate representation languages as there are languages, so we have not really solved the problem yet. But it looks like we have some of these intermediate representation languages that are picking up speed much faster than the others. Circuits is one of these, and I think I don't know exactly, but I think it's connected to LLVM somehow, which means there's a bigger community around it. So I think you have more tooling. And the idea, the benefits of having intermediate representation languages is that this is where you do optimization passes. This is where you can add debug information. This is where you can do some kind of operations that would be very hard to do directly in Verilog, or once you have turned it into a netlist. So hopefully, what we hope to see then is that the EDA tools can natively accept these descriptions directly. And I'm pretty sure that the open source tools will be there first, because they are better at adapting to change. Now, the third thing in this trio of technologies is the PDK. And this, again, is a tightly guarded secret. And if you want to do an ASIC, you have to sign an NDA to get access to the Foundry's PDK. And for those who don't know, a PDK is basically the interface between your design and the foundry, the fabrication technology. So it contains information of how the layers in the ASIC is built up, simulation information about transistors, how fast they are, how much current they draw, all this kind of physical information that you need to simulate and need to do implementations, need for doing implementations, how big is your AND cell, and so on. Let's see, is it 2020? Yeah, I think it's 2020. We had, that was the pandemic, if you remember. So we usually have a lot of conferences, but we moved over to doing a series of video talks called Dial-Up. And the first of these, Tim Ansel, who was then at Google, wanted to present a new project, which was that the Skywater Foundry in the US had decided to open up their PDK, much thanks to Tim, I would say. He's very driving in this. And not only that, Google were sponsoring free shuttle runs for people who wanted to do open source projects on these chips. And that really, really took off. So it was the first time we had a modern available PDK. So people who had never done ASICs before suddenly could just do that for no cost. So this was the MPW, Open MPW project. Google sponsored, Skywater was a foundry, and then a company called eFabless put together a tool chain using OpenRoad and Yosis and other tools, and they call it Open Lane. It's like a more narrow, I guess, OpenRoad. A couple of years later, Google got an agreement with Global Foundries to do the same thing for their 180 nanometer process. And IHP. And the thing about IHP is that it's a European company, or a research institute. So we now have a European technology. eFabless commercialized this into a project called Chips Ignite, where you for, I think, $10,000 could get 300 chips using this same thing. And what happened after that was that a guy called Matt Venn, he realized that, even in an MPW, like a die area, is quite large for many things. So he decided, why not split this up into 400 smaller pieces? And then he could sell each piece for just a few $100s. And I can't overstate how important this project has been. There are almost 2,000 people who have taped out using the Tiny Tape Out project. Matt is, by the way, in Valencia. So one of the stars here in Spain. And so this is one of the chips that was produced. He sells each square at a much lower price. So for like $150, you can make an ASIC. I made one. I got it back this winter. I have not yet had time to boot it up, but the other ones say that there works. And you get it on a board, so you can easily test it. Amazing. This is not something that anyone had anticipated. And once again, if you give the people the tools, they will come up with magical things. So yeah, and this is used by students, makers, professionals, and from the beginning it was digital designs, but they have now verified analog things. They have made ADCs, and yeah, I saw they had an ADC from one project, and then they had a mixer or something, or a PLL from another project. And with that they could, with a bit of software also, they could decode FM radio. So now they're hoping to make a radio on one chip, which is like the next frontier. So there's one thing I haven't really touched upon, which is the fourth ingredient here. I will get to that. If you see, so here in Europe, we have an ambition. We want to be better at making chips. We want to make more chips, have a bigger market share. 20% is the goal. Very, very ambitious. We have been at, I think, 16 or something at some point, but now we're down to like 8% of the market. So 20 is far away, but why not make it ambitious? Motivated by chip shortages and geopolitics, we see that we can't necessarily rely on good relationships with everyone. And the CHIPS Act, or the CHIPS Joint Undertaking, is a big, big EU project. I think it's 43 billion euros allocated for that, to strengthen the European chip industry. Now, this doesn't mean that we need to make everything by ourselves. It doesn't mean that we should make all kinds of chip ourselves. We are in Europe traditionally strong on automotive, mixed signal, RF, but we don't think it's worth spending like doing 2 nanometers CPU, GPU designs. That's important, but we need to focus somewhere, and that's not where we focus. But the important thing, we need to be in control of strategic supply chains. So we need to have everything, even if it's not for every chip. And we see that this is important not only for EU, but for the people living in EU. We have this open letter that was created by my FOSSI Foundation colleague, Stefan Valentovits, together with some other people. We collected more than 500 signatures from academics all over Europe who said that it's important that we invest in open source EDA technology. And I know that I think at least one in the room has signed this, right? Yeah. And so the FOSS Foundation was asked to make a roadmap for the EU to show where we should focus our efforts, what activities needed to be done for open source silicon in the EU. And those calls are coming out now. Consortia are being formed as we speak to answer these calls. So it's right now 20 million euros, we know that. We're hoping, which should be matched by co-funding from the national agencies as well. Problem: who should do all these things? It turns out we have a huge shortage of people. That's you. We had a presentation at ORConf, which is one of the conferences we run last year, where they collected some information that around 100,000 employees are missing in the semiconductor industry only in Germany, France, Netherlands, and Italy. And we believe it will rise up to 130 people in 10 years, because most of these people are old. So we need to attract new people. We need to get more people involved outside also of the traditional like people who are coming into this world. And we need to add ways for that to make that possible. And open source is not the full solution, but it is part of the solution. Make it easier for people to experiment these things. Make it more welcoming. Make sure that we can advance things in areas where it has been lacking. Make sure that we can include more people into these efforts. Also do more hands-on training. And the more hands-on training, if you do hands-on training with the proprietary technologies, it will very quickly become expensive and cumbersome and complicated. If you have to sign an NDA and wait for 6 months to get access to the tools, then it's very different from starting tomorrow. Andreas Olofsson, who was leading DARPA, one of the projects at DARPA that produced Open Road, he said the same thing about the US, lacking a lot of people. And open source is a good entry point for this, to help people getting involved in this. And you can also get involved. I mean, there are many ways to getting involved, and sometimes it's hard to find the right way in. But just a few things I would like to mention here is that we run our monthly newsletter, which is called El Correo Libre, because we had a site called LibreCourse. I thought it was funny to call it El Correo Libre. Yeah, you can contact us as FOSSA Foundation. And we also, for the past 10 years, we have been participating in Google Summer of Code. I don't know, does everyone know what Google Summer of Code is? You can slightly shake your head if you don't know, and I will explain. Okay, so Google Summer of Code is a project that is run by Google, of course, where they provide funding for students to work on open source projects. So it starts by organizations like FOSSA Foundation or others who are organizing open source projects. They say, hey, we have this project and we can supply a mentor for this project. And then students can apply for this project, or they can come up with their own projects and hopefully find a mentor for it. And then Google will fund their work on this project. Traditionally it's been over the summer, but it's now spreading out over the year because they realized that some people, different countries have different school years, basically. So we have had a lot of good students who have produced open source. This is primarily to get people involved in open source silicon and make sure that they get a bit of money for doing that. So in many ways, open source, but the chip design industry has a bit of a problem. It's kind of old. There are not as many young people as we would like coming into this area. But I would like to remind you that this once was new as well. And I really like this quote. It's from Mead and Conway's classic Introduction to VLSI book, which is, I think, from the beginning of the 80s, when very large scale, or is it VLSI stand for? Forget it. VLSI, you know what that is, when that was new. And they saw that, wow, this is a new thing. This opened up so many new possibilities. And they were just wondering, where will this lead? And I think what we have seen now is that we have stagnated a bit. But I think open source is where we will find new energy and find new ideas. And with that, I would like to thank you for your attention. Thank you. Questions?
Why it is still difficult to take a PhD, a Verilog code, RISC-V, and map it to, for example, a Xilinx 7 series. It's not so easy to use the full open source stack and map it. For example, using the VROLF and map it to a Xilinx 7 series, you need Vivado. And why is so difficult to fill this gap?
I think in many cases, I am not sure actually you need Vivado anymore, because the open source tools have advanced. But I know that some part of Werewolf is written using some obscure system Verilog constructs, which are not yet supported by open source. So that's one thing, that the system Verilog standard is extremely complicated, and that has been a hinder for many open source tools, and which is also one reason why people are inventing new languages, because they realize that this, I mean, have you seen the system Verilog standard? Like, I think I saw some figures that, like, the Python standard has 37 reserved keywords, and the C standard had like 50, and system Verilog had like 300 reserved keywords. It's a massive standard, and it's way too complicated. So that is one thing that makes it harder to use open source tools. And I'm not sure if that is answering your question, but that is one thing that I know why the open source tools are not yet where the proprietary tools are, and that is really language support.
And another question is why, for example, FuseSock and other tools are stuck with Wishbone instead of using other kind of interconnect.
Why is using Wishbone? Yeah, so then we need to go back in time. So in 1999, a bunch of Slovenian students, they created a CPU called OpenRISC. And then they put it on a website that they called OpenCores. And they created a bus called the Wishbone bus. And at that time, this was the open bus that existed. This was before anyone had even thought of taking like APB, or I don't know if APB existed even then, but AXI certainly didn't. And many of these buses also have and had licensing restrictions. So for the longest time, Wishbone was the natural bus technology for doing open source design. I think we're moving away from that actually. But the stuff you find on OpenCores is mostly Wishbone compatible, because that was what was available at the time. In my latest project that I did for a customer, we decided to go away from the Wishbone bus and make APB instead, because it kind of filled the same slot. But it's, yeah.
Because, for example, last year I tried to reuse Ethernet code, Ethernet controller, and it was not easy to find something else than with Wishbone interconnect.
Yeah.
So if you have to connect for another kind of microcontroller, or you are stuck, you need a bridge to interconnect whatever with Wishbone, and this is a limitation.
So I'm actually the maintainer of the Ethernet Mac on OpenCores. Well, not on OpenCores, because that site is dead, but that came from OpenCores. And I have not touched it in many, many years. It's not one core I would recommend. Also funny, I was at it was some of the proprietary companies. They were demonstrating their tools, and they said, "Oh, our tool is so good at finding bugs." And I had found a bug in that Ethernet Mac, and I said, "Okay, why haven't you reported this to the maintainer?" But anyway, yeah, there's a project called Corundrum, I think, which I would recommend. This is a modern, high-performance network stack. I think it has an Ethernet Mac and it has other things. I think it goes up to 10 gigabit or even 40 gigabit, I'm not sure. And that certainly has an AXI interface. It's a guy called Alex Forensic who makes a lot of good IP available and also AXI interconnects. He also did a CocoDB AXI VIP basically that I'm using quite a lot nowadays. Okay. I can give you the link.
Okay, thank you.
But yeah, generally it's a problem with quality control and maintenance, and so that's it. I can't stress how important maintenance is. And if you have any political leverage make sure to help us find a way to sustainably maintain things. Because as I said, I have way too many projects. I have no time. I would like to be with my family. I can't maintain open source projects for free. So it really relies on people having time and funds to do that.
Thank you, Olof. I'll ask you two questions as a RISC-V ambassador.
Yes.
First, when I was at the RISC-V Summit 2 years ago, I think, or 3 years ago, they were mentioning they were quite worried about the fragmentation problem they were facing in different things, RISC-V extensions, development of cores, and so on. And they were saying that we're starting to try to coordinate all these efforts. So do you think at this time, are they succeeding in that? And second question is, how do you see the future of RISC-V in industry? Not academia, where I think it will keep growing, but also industry.
So the first thing, yes, there's always a challenge because you want to move fast, but you also want to make sure that you don't do anything stupid, because once you have written a spec, it's there. It needs to stay. So what they have done basically is, from the beginning they thought we need a handful of extensions. We need the C extension for compressed instructions. We need the A extension for atomic instructions and the F extension for floating point. But what's happened in reality is we have hundreds of extensions. We have so many. It's like extension can be an instruction that provides hint that something takes longer than some other instruction. It's like these very, very narrow things, but they are needed for some applications, or at least for some applications to work well. But once you have this, then you can just grab a handful of these and you take the ones that are more relevant. When you see the bigger pictures, if you take a group of these that you see, okay, these are good to have, this is like standard things, then you put them in what they call a profile. So that you have, a profile is basically a set of extensions that are required, like a group of extensions. And the reason for that is that if you do any software, you need to rely on certain instructions being there, because otherwise you would need to recompile for every target. So the profiles is meant to solve that. They have the RV, don't remember the naming exactly, but I think they have the RVA23, which was ratified in 2023, and is for application processors. So basically your smartphones or your Linux capable systems, and that has a bunch of these extensions that are relevant. Then you can of course add more extensions, but then your software cannot rely on them being there. So that is one way of managing that. And for RISC-V in the industry, I think I like to divide it into different areas. If we look at the tightly embedded thing, deeply embedded thing, like we have battery controllers or small IoT devices and things like that, where unit cost is important, I think we will see RISC-V. I think for design starts, I don't see why you would go with something else than RISC-V there. Typically, these are not performance constrained, but more power constrained, and it's more like implementation details, how you do things. If we look at like smartphones or bigger things, tablets, laptops, things like that, then we are getting into a space where you need performance and you need also need have power concerns. I think ARM is very, very strong there right now. I think it will take longer time. We are starting to see some things, but they are like closing in on ARM, but still ARM is where things are happening right now. And also there's an installed base. You have so much software that is written for ARM. Just like if you look at the desktop market, where you have the reason why Intel and Windows is still going strong is because you have all these old things that you still expect working. The desktop market, I think, is dying because people are the traditional. You have heavy computation things, and then you have your personal devices. The desktop market is going away. So I don't think RISC-V will ever go in there because I don't think it's much to do. And then on the high-performance computing side, which is, I would say, the last, together with data centers, this has traditionally been dominated by like power and x86, and together with the GPUs from NVIDIA, for example. And ARM has, for the past 10 years, taking a lot of place there. You can now, with the big cloud services, you can now run on ARM cores. And this has opened up the way for more architectures, I think, but I think also that the design, it takes a long time to do designs that are that performant. So we will see, we have, for example, Rivos, Ventana, we have a couple of those that are coming, but they have a tough competition. So I think that's kind of my overall, but it's here to stay, definitely. It's like, if you look at compare with the network stacks, in the 80s we had a lot of different network stacks. But then everyone just, screw it, we go with Ethernet. Because it was open, you could do anything with it, you could, you didn't need to pay anyone a novel or whatever, a license to use it. It was just easy. It's just the path of least resistance, I would say.
Muchas gracias.
Thank you very much. Very interesting presentation. I have just one question regarding Brelator. I ask if this tool has any capability for code coverage and any kind of metrics to evaluate the quality of the code, functional coverage, property coverage, and all this stuff.
So you know? I missed which tool you were talking about, sorry. Which tool were you talking about?
Verilator.
Yes, I think it has code coverage metrics built in. I have not used them myself, but I'm pretty sure it's there. I can't say anything about the quality or how useful it is. What was the other thing you were? Was it equivalence checking?
Code coverage, functional coverage, conditions coverage, all these kind of metrics that is usually used by functional verification people to evaluate the quality of the verification.
Yeah, so I think there is support, but I can't say anything about how good it is because I don't know.
Okay, thank you.
I can ask Wilson Snyder, who is.
¿Algo más? Bueno, pues muchas gracias. Encantados de que hayas aceptado nuestra invitación. Muy interesante todo.